Hello, my name is Jeff Messier. I'm a professor of electrical and computer engineering in the Schulich School of Engineering, and this is the SPICE simulation tutorial video for module number 1. And just as a bit of background, since this is our first SPICE tutorial, SPICE is a circuit simulator that's been around for many years. It started as an open source project from the University of California, Berkeley. And it's since evolved into a number of different versions. There's PSpice, which is now a commercial version. There's LT Spice. There's various simulators out there. And most of the simulators out there basically allow you to draw a circuit schematic using the symbols for resistors and voltage sources and stuff like that. And then what that simulator will do is generate something called a SPICE Netlist, which looks like basically sort of a programming language for describing a circuit. And then the SPICE simulator operates directly on that netlist. Now, for this class, since this is your first introduction to SPICE, I've decided to work with the netlists directly. And this is the way SPICE was originally done. And I think there's still value to working with the netlist because it gives you an idea of sort of what's going on under the hood of some of these other simulators. And there are things that you can do with directly editing netlists that are sometimes hard to do with a more graphical simulator, depending on your application. For example, SPICE netlists are essentially a kind of programming language, and so you can do things like for loops, for example, if you want to experiment or investigate circuit performance for a range of resistance values. And sometimes that can be difficult to do with a graphical simulator depending on the circuit that you're working with. The other thing is the circuits that we're going to be dealing with in this class are quite simple. And so writing a netlist by hand is not particularly difficult. You really need to resort to the graphical simulators when you've got larger circuits that contain, hundreds of elements potentially. So the simulator that we're working with then is called NG Spice. And NG Spice is an open source version of SPICE. You can download and install it on Linux, Mac, and Windows. I'm going to be showing you the demo on a Mac, but I'll be running it using basically a Linux terminal on top of a Mac. This works essentially the same way on a Windows computer if you install it as well. And so what we're going to do with this first tutorial is basically kind of see an example of our first netlist, go through kind of some syntax things, and then in our next tutorial, the one that's coming up, we'll talk a little bit more about exactly what kind of simulator SPICE is. So just to begin, in the Module 1 folder for this class on the D to L page, if you're registered in this course, there will be two .cir files. Each one of these .cir files describes a circuit. The first one is a simulation for a non-ideal voltage source, and the second one is a simulation for a non-ideal current source. And we talked about non-ideal voltage and current sources just now in our in the online lecture for Module 1. And basically the purpose of these simulators is to figure out, how much waste there is due to these internal resistances. How much power is being dissipated internally inside our sources relative to the amount of useful power that's being delivered to our load. And so let's look at the non-ideal voltage source example first. And so what I'm going to do is I'm going to go into the directory that contains the .cir files. And so we can see a few of them here. Non-ideal isource.cir and non-ideal vsource.cir are the ones that we'll be working with. And to start the simulator, I just type in ng spice. and you get this terminal. If you're running a Windows machine, when you start ngSpice, I believe it just puts you directly into this terminal. And then you need to open up the NonIdeal vsource.cir file using some kind of text editor. In my case, I'm using Emacs. And so just to kind of go through the structure of a Netlist file, it starts out, the first line is always just a comment line indicating what the circuit is for, or what it represents. In our case, this is our Module 1 simulation for a non-ideal voltage source. After that, every line that starts with an asterisk is a comment line. So just like a regular programming language, Spice allows for comments. And so the first portion of the Netlist file, basically this portion, is where we're going to define our circuit elements. And then between the .control and the .nc statements is where we're going to perform our simulation. Okay, so I find when you're working with a netlist, particularly when you're getting started, after a while you don't need to do this, but when you're getting started, it is useful to draw your circuit that you're simulating. And as I've done here, this is our non-ideal voltage source. And in our non-ideal voltage source, we have our ideal voltage source, our internal resistance, and our load resistance. And one thing you need to be aware of about Spice is that it is a nodal simulator. And I'll talk more about that once we review nodal analysis in the next lecture module. But for now, it basically means that we have to label every node with a unique number. And a node, just as a bit of a review, a node is anywhere, the wires from multiple circuit elements join, right? And so our first node is where the voltage source joins up with the first connection to the internal resistance, and I've labeled that as node number 1. Our second node is where the internal resistance connects to our load, and the third node is where our load and our voltage source connect to ground. Now, in Spice, you can actually call your nodes whatever you want. You can even use letters or words to describe your nodes, with the exception of the ground node. So the node that's connected to ground always has to be node 0. And so basically, if we look at the format for our netlist, when we create our ideal voltage source, we start with the letter V. All voltage sources have to start with the letter V. After that, you follow it up with a unique identifier. So this can be a number, it could be a word. For example, we could call this V source if we wanted. We could call this V99 if we wanted, just as long as it doesn't match any other source in your simulation. The next thing we need to do is specify the connections, basically, of our voltage source. So the two nodes that our voltage source is connected to. So our positive terminal is connected to node 1. Our negative terminal is connected to node 0. We're doing a DC simulation here, so we specify DC, and then we just give our voltage value, 1.5 volts. And you actually don't have to specify the units if you don't have to specify the units if you don't want to. You can just do 1.5. The resistances have a similar format. Any circuit element that starts with R has to be a resistance. After that, you give it a unique identifier. In this case, rather than using a number, I've decided to use the word int as our unique identifier to represent the fact that it's the internal resistance, right? So this is the resistance that we're representing there. We then specify the nodes that our resistance is connected to, nodes 1 and 2. Then we give our resistance value. And as I said in the lecture, internal resistances for voltage sources are usually pretty small. So I'm using 0.15 ohms as the value for like a typical AA battery, for example. And finally, we have our resistance that represents the load of our circuit, our load. And it has the same format as our internal resistance. We have to start with R because it's a resistance. Then we give it a unique identifier. In this case, I call it load. It's connected to nodes 2 and to 0. And its resistance value is 1,000 ohms. I could also do 1K because SPICE represents the prefixes, milli, kilo, stuff like that. Now, if we look at our simulation section, the two letters OP causes SPICE to do what's called an operating point simulation, and that basically determines all the DC voltages and currents in our circuit. So it's just these two little letters OP that actually cause the simulation to run. The rest of it is basically interpreting our results. And I'm getting a little fancy here, I guess. I'm using variables. You don't always see variables used in SPICE, but I do like to think of SPICE as a programming language. And so I want to create a variable that contains our load resistance value. So I use the special command let, and then it allows me to define a variable rload that's equal to 1,000. You'll note that I'm using the same name as I used for the circuit element in our circuit section. I don't have to do that. None of these circuit elements actually carry into the control section, so I could use the same. I could use rload. I could use something different. It doesn't matter. The internal resistance is 0.15, and then I want to figure out the power that is dissipated in the load compared to the power dissipated in the source. And we know that the power dissipated in a resistor is equal to V squared divided by R. And so the power dissipated in the load is the voltage at node 2 squared divided by the value of the load resistance. The power dissipated in the internal resistance is the voltage across the resistance, so the voltage between nodes 1 and 2. And so, or squared divided by that resistance. And you'll notice a difference in my notation here. I could have done this. Well, when I want the voltage just at a node, I just give V and then I give the identifier for the node. So in this case, the number 2. So this is the voltage at node 2, always relative to ground. And so any voltage in SPICE is always relative to ground unless you specify otherwise. So V2 is the voltage relative to ground, which is what I want for my load resistance because I want the voltage between nodes 2 and node 0. For the source, however, I don't want the voltage relative to ground. I want the voltage relative or between nodes 1 and 2. And so I just give, again, I use the letter V to extract a voltage, and then I just type in the nodes across which I want that voltage to be taken, right? So I want the voltage across nodes 1 and 2, and so that's the terminology that I use there. And so V squared divided by R, and then I just calculate the percentage waste just using the formula for a percentage difference. So it's how much load is dissipated in the source divided by the total amount of power dissipated in the circuit, the load plus the source. And then I use this echo command to print out the results. And so if we go into our terminal, the way that you run a SPICE simulation is you just type the name of the script. So NonIdeal v source.cir, hit enter, and then you get some some messages. Our circuit is module 1, non-ideal voltage source, which is what we wrote in the very top of our circuit file. It tells us the temperature that it's doing the simulation at, and that's important if you're simulating noise, which we won't be in this class. And then we get number of data rows, which is just an overhead message. And here we get our output statement. So percentage power wasted in source is only 0.01%, right? So in the end, when our source is driving a 1 kilo ohm load, only 0.01% of the power is getting wasted in the load. Now, as we decrease the resistance of our load, this is going to change. So let's decrease the resistance of our load to 8 ohms, which is a typical value for a speaker, which we'll be working with in this class. And then we run the simulation again. And we can see that the percentage of power wasted in the source jumps up to 1.8%. So a little higher, I mean, not zero, almost 2%, but still not a huge amount. So what we can conclude is that we don't really have to worry too much about the power wasted in our non-ideal voltage source, at least for these parameters. And hopefully this has given you an idea also of some of the notation that we use in a SPICE simulation. Okay, now let's take a look at our non-ideal current source. So this is the file for a non-ideal current source. And it's, again, got exactly the same format as the voltage source one. The first line is just a little comment saying this is now our non-ideal current source simulation. The first part of the file specifies our circuit elements. The second part of the file specifies the simulation and the analysis that we're going to do. And in this case, I'm creating a non-ideal current source. So over here is a picture of our circuit. And we have a non-ideal current source I1. We have an internal resistance in parallel with the ideal current source. And then we have our load resistance. In this particular case, we only actually have 2 circuit nodes, right? So we've got the connection at the top, which connects our ideal current source, the internal resistance, and the load. And at the bottom, we have ground, which again connects all 3 of our elements, because in this particular case, everything is in parallel. And so if we look at our SPICE file, this is our comment because it starts with an asterisk. All current sources start with an I. We then have our identifier. I chose the number 1. Again, I didn't have to. Then our 2 nodes that we're connected to, nodes 1 and 0. We are doing a DC simulation, and I'm going to simulate 1 amp of current. Our internal resistance is going to be 1 mega ohm. Oops, that should be int probably. 1 mega ohm. And our load, let's start out with a kilo ohm for our load. In our analysis section, again, we do an operating point simulation, and then I use some variables here to do some analysis. 1 kilo ohm. The power dissipated in the load is V squared divided by R. We're interested in the voltage at the top of our resistance relative to ground, so I only have to give the first node number here. And the source is also connected to ground in this case, so the power dissipated in the source is just V1 squared divided by the resistance. And then we do our percent waste calculation, just like we did before. And we're ready to go. Oops, I have a mistake here. The internal resistance is 1 meg and our load is 1 kilo ohm. So to start the simulation, we just type the name of our simulator here. I actually ran it with the mistake, so let me run it now without the mistake. Ideal source.cir. And we get the message saying the script file that we're running, some overhead messages talking about temperature, number of data rows. And here's our waste message. The percent power wasted in the source is less than 1%. And so here we have not very much waste, driving a kilo ohm of resistance, which is actually a fair bit of resistance for most current source applications. Most LED lights would probably have a resistance of less than a kilo ohm. But just for the sake of experiment, we can increase our load to 1 mega ohm. So it's equal to our internal resistance. And as you would imagine, looking at our diagram, if the internal resistance and the load resistance are the same, they're basically going to draw the same amount of current. And so if we run our simulation again, we see that that's the case. The percentage of power now wasted in the source is 50%. But like I said, I'm not aware personally of too many applications where we would be driving a mega ohm of resistance using a current source. So for most cases, like particularly LED lighting, we should be in good shape. So that's the end of the tutorial, and hopefully that gives you a little bit of an intro into what these Spice Netlist files look like. We're going to be doing some more tutorials as we move through these modules, and they'll illustrate, hopefully they'll keep illustrating how Spice works, and you'll get more and more comfortable as you work through the examples.